record on this computer. Thank you. Always a good thing to ask me. Now I've got homework 1 and homework 2 spread out so you can read them, but we can also talk about anything else you'd like to. But I did notice certain problems with some of the homework questions. And actually, I may do one of them first because this is one that I noticed a lot of mistakes on. And partly it was a unit problem. The kinetic energy of the alpha particle. This is the one Ernest Rutherford had the people shooting alpha particles at gold nuclei. The gold nuclei were in a foil, a very thin foil. Gold can be beat into an amazingly thin foil. The people who do gold leaf in old books, it's so thin you can almost read through it. And there was a reason that they used it that thin, but anyway, they shot these alpha particles at gold nuclei. They didn't realize they were shooting them at nuclei at first. Actually, this was when the nucleus was discovered. But anyway, they shot them at it, and the gold nuclei are part of the solid. You can think of the thin foil as being a solid, and they're pretty much fixed in place. Plus, they're way more massive than the alpha particles. So it would be like bouncing ping pong balls off of a bowling ball, I guess. And the bowling ball's not going to recoil much when it gets hit by a ping pong ball. However, the alpha particles had a kinetic energy of 5.04 MeV. Now, that's a unit of energy, and the M means it's a mega. An electron volt is a unit of energy. And so the kinetic energy of those alpha particles when they're far from the nucleus is 5.04. Most people got that the capital M stands for 10 to the 6th, so it's times 10 to the 6th electron volts. But to do this problem, we need to convert those electron volts into joules. And so you have to know that there's a conversion factor between the two, and 1.60 times 10 to the minus 19th joules is equal to 1 electron volt. So this is just a funny looking one for unit conversion. But you have to do this to be able to get the energy in joules and get rid of those electron volts. Because electron volts, well, they're handy for electron energy transitions and energy of photons and stuff like that. They're not convenient for when you're talking about a conservation of energy for something that has a mass in kilograms or anything else. So you have to convert to joules, which are kilogram meters squared per second squared. So that's all you have to do first. 5.04 to the 6th. Can almost do it in my head. It's going to be about 8, I think. Whoops. If I can type it into my computer right, or calculator right. 8 times 10 to the minus 13th, maybe. Let's see. Oops. It would help if I hit multiplication instead of addition. There we go. 8.06 times 10 to the minus 13th. So, okay. So that's the kinetic energy of the alpha particle when it's far from both the radium that it came out of and the gold nucleus. Now, when it's far from that gold nucleus, It's not going to have any electric potential energy. And so this is an energy conservation problem. We're going to think initial equals final on here. The initial energy is just that kinetic energy, so I'm just going to write it as Ke. And at the end, the alpha particle is going to come to rest momentarily, and so it'll have no kinetic energy, but it will have electric potential energy, and we're supposed to figure out how close it gets. Well, when two charges are a distance r apart, they'll have an electric potential energy of K sub e Q alpha and QAU divided by R. And that's the electric potential energy. It's the charge on the alpha particle, the charge on the gold nucleus, and so forth. So to solve this thing, we know how much that's going to be. What I don't know at this point is, well, I know the charge on an alpha particle. It's 2 electron charges. If I remember right, gold is, let's see, element number 79. Geez, I just had to track the periodic table down in here earlier today, but I think it's element number 79. Yes, gold is a charge of 79 of those. So let's just plug in the numbers here. We'll have 8.06 times 10 to the minus 13th joules equaling K sub E, 8.99 times 10 to the ninth. Let's see, Newton meter squared per Coulomb squared. On the bottom, we're going to have this R, which we don't know. And we're also going to have the charge on the alpha particle, which is 2 times 1.60 times 10 to the minus 19th coulombs. And then the charge on the gold is 79 times 1.60 times 10 to the minus 19th coulombs. By the way, it's no accident that an electron volt is equal to 1.60 times 10 to the minus 19th joules, because an electron volt is the kinetic energy that an electron would acquire if it's accelerated across a potential difference of 1 volt. And so this EV, this is actually a Q delta V, but the Q in this case is just the charge on an electron. The delta V is 1 volt, so that's why it's called an electron volt, is because it's the electron charge times that, but we just call it an EV. And the kinetic energy it would acquire when being accelerated across that much potential difference is that much energy, 1.60 times 10 to the minus 19th joules, because that's the Q. And if you multiply it by 1 volt, you get a, let's see, Coulomb volt, which is a unit of energy. Remember, a volt is a joule per Coulomb. So at any rate, you have to multiply this together and solve for R. And R is just going to equal all this stuff divided by this. So if I plug that in, we should come up with something more reasonable for a separation between the two. 10 to the minus 33rd meters is not reasonable. The nucleus of an atom is about a few things times 10 to the minus 15th meters. The proton size is roughly 10 to the minus 15th meters, and 10 to the minus 33rd meters would be not reasonable. So anyway, times. Okay, and I punched something wrong into my calculator because I can see I got an unreasonable number. I'm not sure where I went wrong. Let's see. I'll check out my equation here. Whoops, one place I went wrong was that could be where I went wrong. Um, well, that's one of the places, 8.06 times 10 to the minus 13th. Let's see, 1.6 times 10 to the minus 19th. I have that. Oh, okay, this is more reasonable. About 4.51 times 10 to the minus 14th meters. So this is almost touching the nucleus of the gold atom, but stopping just short. And so the nucleus of a gold atom, let's see. Yeah, I don't know. I can't remember. 1.2 Fermi times, I guess I can figure it out roughly. Um, yeah, actually, this is about 6 times as large as the nucleus of the gold atom. So not that you would have known that, but this is a more reasonable value for the close approach distance. So question 3 on the practice test. Oh, crud. Um, let me track that one down. I didn't bring that or didn't print it, but I can get it real quick. Was that the 2018 test? Does anybody remember? I'm guessing that's what it was. Let's see. Okay, and if I print off the wrong test, I'm pretty sure it's 2018. Is question 3 to determine by integration the electric potential at the center of curvature of a thing? Yes, yes. Okay, good. I appear to have the right test then. And hopefully my printer still has paper in it. Okay. Anyway, there's the question. I think determined by integration the electric potential at the center of curvature of a thin strip of insulating material bent into 3/4 of a circle with a charge per unit length of 4.05 picocurie or picocoulombs per meter. And the radius of curvature of the strip is 7.83 centimeters. So this may not be as hard as you think it is. It is easier to calculate electric potential than electric fields. On your first homework, you had one where you calculated the electric field of a charge distribution. But for a potential, first of all, we're going to assume that V equals 0 at infinity. And then we can just say that the potential at P, V sub P, is going to equal an integral over the charge distribution of K sub E dq over R, where R is the distance from dq to point P. Well, we're lucky here because P is at the center of curvature of this entire thing. And so everything is going to be that distance R away. And what we actually have here, K sub E is a constant. We can pull that out of here. And V sub P in this case is going to equal K sub E over R. And then I've got dq left inside. And that's all. So I just have to integrate over this charge distribution. And I think dq, just imagine some little tiny slice of this thing that is going to be, this could be d theta. This would be R. This little chunk here is going to have a length of R d theta. So we'll have that showing up in here. And we'll have to integrate the angle theta. So what have we got here? Vp is going to equal K sub E over R. dq will equal lambda ds, or lambda times the length of this thing. It'll be lambda R d theta. Lambda, can't read that very well, but that's it. And so I'll have lambda R d theta still in the integral, but lambda and R are constants. So we'll actually get Vp is equal to, well, the R's divide out, and I'll have K sub E times lambda times the integral over d theta. So I had to start with this expression. I had to recognize what I had for constants. They can come out of the integral. Then I had to come up with an integratable value for dq. Actually, you could almost get away. You could integrate dq and call the result capital Q, which would be the charge on the entire thing. And in that case, you'd, well, just have to figure out the length of this, which is going to equal this angle all the way around times R. And actually, I'm going to let theta equal 0 right here. And at this point over here, I'll measure theta in the clockwise direction. Let's see, this would be pi. This is going to be 3/2 pi. So theta equals 3/2 pi when we get over there to there. So I'm integrating from 0 to 3/2 pi. And integrating d theta over that, I'm just going to get 3/2 pi. So this will equal 3/2 times pi times K sub E times lambda. And now I can plug in numbers and see what I'll get. The electric potential there should be 3/2 times pi. Those are just numbers. K sub E, 8.99 times 10 to the 9th Newton meters squared per coulomb squared, times lambda, which they said was 4.05 picocuries per meter. That would be 4.05 times 10 to the minus 12th coulombs per meter. And let's see, this coulomb will divide with that coulomb. This meter will divide with one of those meters, and I'll have Newton meters per coulomb. A Newton meter is a joule per coulomb is a volt. So unit-wise, I end up with volts. And whatever it turns into, 3/2 is 1.5. And I think I get 0.17. How many sig figs? I can keep 3. 0.172 volts. So that would be the potential at the center of that thing. Any questions on that one? I'm curious. Let's see. If I just called this integral capital Q, so I would end up with K sub E capital Q, the charge on the entire thing, divided by R. And Q would equal the radius of that thing times 3/2 pi times lambda. So that would give me K sub E times R times 3/2 pi times lambda. And I had an R on the bottom, so those divide out. And that's the same thing I had here, 3/2 pi times K sub E times lambda. And so that was a different way of doing it. If you just jumped immediately to this thing. So 2 ways to do that problem. Oh, I need to click that and get rid of some of the junk in the margins. Okay, any other questions? Other questions on either the homework questions or the practice test. Now this one says spring 2021 on it. Huh. But I think I reused it that spring. What was our first quarter of teaching stuff online, being forced into it without any practice ahead of time. Oh, practice test question number 5. Okay, let me track that down. Whoops. The worksheet that is due tomorrow, number 2. Okay. Let me find practice test question number 5 first, and then I can look at that other stuff. Okay, 3 capacitors are connected in series, and this combination is connected to a 12-volt battery. Okay, the values of the capacitances are such that C3 down there, this is equal to 3C1. So this is C1. This one is 3C1. And this one is 2C1 as far as the values of their capacitances. And then rank the capacitors in terms of the potential difference across each capacitor from greatest potential difference to least potential difference. And you can use delta V1 for the potential difference across C1. Okay, well, capacitors in series, what is it that is the same for those capacitors in series? Anybody know? Go ahead and type it into the question or the chat if you happen to know. Not the voltage, okay, not the potential difference across them. In fact, that's what I'm supposed to be ranking here. But there is something that is the same for all 3 of them. And it has to do with the fact that if I blew those things up, so here's the first capacitor, this is C1, and you can partly understand it by looking at this picture. This would be C3 here. And they're connected. You've got them wired in series ahead of time. And then you connect in this 12-volt battery here. Okay. And so now maybe there was a switch up here and you threw the switch with that 12-volt battery in there. Eventually, this capacitor is going to have some positive charge on it. This capacitor down here at the bottom will have negative charge on it. Okay. But things will happen from here on down to here. These things are isolated from the rest of the circuit. There's no conduction across the plates of a capacitor. Okay. Now, with these positive charges here, there will be an electric field here pointing in that direction, and negative charges will be attracted to this bottom plate here. So you'll have negative charges here. And in fact, the amount of negative charge here will equal the amount of positive charge here. But where did that negative charge come from? It came from this plate here, which used to be neutral, but it just lost a charge Q going up to here of negative charge. That leaves behind positive charges. So you've got a charge plus Q up here. You'll have a charge minus Q down here. On this middle capacitor, you'll have the same charge on the top plate of it that's plus Q, and the same charge on the bottom of it that's minus Q. And similarly with this one, you'll have a plus Q on top and a minus Q on the bottom. So capacitors in series all have the same charge on them. So that's something that's going to let us figure this thing out. Now, I can do something here where C1 is going to equal the amount of charge that's on C1, Q, divided by delta V1. Okay, C2 will equal the amount of charge on it divided by delta V2. And I'm not trying to distinguish between the charges on the capacitors because it's the same on all of them. And C3 will have the amount of charge on it divided by delta V3. Well, it's asking me to rank these capacitors by their potential differences. So I'm going to solve for the potential differences, and they gave me enough information to figure out the question from that. So delta V1 will equal Q over C1. Not so bad. Delta V2, I just did two algebra steps there. I multiplied out from underneath by delta V1 and divided by C1. So be careful when you're doing that. Delta V2 will equal Q over C2, but C2 is 2C1. So I'm going to have Q over 2C1, which is 1/2 times Q over C1, which is 1/2 of delta V1. Well, that's interesting. And delta V3, that will equal, let's see, Q over C3. But C3 is 3C1. So now I've got Q over 3C1, and I can rewrite this as 1/3 times Q over C1, but Q over C1 is delta V1, so this one is 1/3 of delta V1. So which capacitor has the greatest potential difference across it? Well, it's V1 or C1. Okay, its potential difference is Q over C1. In between, or the one with the least, is capacitor C3, because the potential difference across it is 1/3 delta V1. And in between is C2, which is 1/2 delta V1. So, and my reason for ranking the capacitors this way, well, they all have identical charge, but the potential difference across a capacitor, the delta V, is always the charge divided by the capacitance. And so the one that has the smallest capacitance is going to have the largest potential difference because the capacitance shows up in the denominator. So it's kind of a tricky problem. Let's see. Oh, Alyssa said it's the charge. Okay, somebody got there eventually. Yes, thank you. Okay, let's see, Alyssa, you had a question on something. I need to scroll up to see the worksheet that's due tomorrow. You mean homework 3? Okay, let me go print that off. Um, hopefully I've got it handy. I can get the mouse over here. Let's see, homework. Winter, spring 2024. And it's actually just on capacitors, not things and electric field. Oh, there was another. Actually, if I change the view here for a second, as I was looking at this the other day, I found another error that I hadn't fixed as far as an equation goes. Yeah, it is on this thing in problem 1, there's supposed to be an equation here giving you the capacitance of a parallel plate capacitor, and I think it only had C equals or something, and it was another one of those software failures because I stopped paying the dues to math type, I guess. So anyway, the capacitance for a parallel plate capacitor is epsilon naught A over D. And so that's something you'll need. And now I forgot which question you were asking about, Alyssa. Oh, number 2. Okay. A solid slab of metal is placed between the plates of a capacitor without touching either plate. Does the capacitance increase, decrease, or stay the same? Okay, this one, I don't expect you to be able to answer this without drawing the situation. So I'll do that here, and maybe that'll help. So imagine that here's your parallel plate capacitor, and have something like this, and it's got an area A on top, and it has a separation D between the two plates. And so the original capacitance, C initial, would be epsilon naught A divided by D. So that's the initial capacitance. Then you take this chunk of metal and put it between the two plates. Okay, a conducting slab of metal, which is as good as changing this into a situation where you have two capacitors in series. Okay, where this is going to be a C1 and this is going to be a C2. Okay, instead of having a thin wire here, you've actually got a slab of metal that's the conductor. But when you put this thing into a circuit and charge it up, you're going to have some amount of positive charge on this upper plate here, some amount of negative charge that's on this one that'll match that one. That negative charge had to come from this bottom plate.
We're still on the
Still on that thing. Sorry, gotta go back. So you don't have a clue what I'm talking about. Better back up a bit. Visualizer, there we are. Okay, anyway, here's what the situation. You initially you didn't have this slab of material in here. You had a plate up here, a plate down here. It's a parallel plate capacitor and it's separated by a distance d. And then you stick this slab in here that, let's just imagine that it has a thickness x, and it turns out it doesn't matter what the thickness happens to be, but I just made it big enough to draw easily. So now I have two capacitors in series. And so if I call this top plate and the top of this slab C1 and the bottom of the slab and the bottom plate of this thing C2, I'm going to have, I don't know, I can call this distance here maybe, this was total distance D. This is going to be D1 here. And this will be D2 here. Okay. So, is the capacitance of this combination less than the initial capacitance, more than the initial capacitance, or the same? Well, you'll have to solve this, but here's the deal. They're two parallel plate capacitors. So the capacitance of the top one is going to be, let's see, it'll be epsilon naught A over D1. The capacitance of this one, C2, will be epsilon naught A over D2. And I think you know the expression for two capacitors in series to calculate the effective capacitance. And here's a hint that D1 plus D2 plus X is going to equal D. And you're going to be able to use this in figuring something out. In fact, D1 plus D2 is going to equal D minus X. And so there's a hint. And between using the way to figure out the effective capacitance of two capacitors in series, and then maybe trying to add some fractions together that might have different denominators. Let's see, and then using this, you'll be able to compare your final capacitance, or the capacitance of this thing, with the capacitance of that thing, and make a choice based on that. So this is kind of a fun one. Maybe. Any other questions? When I was grading homework 2, let's see. I don't know, that one about the gold nuclei and the alpha particles was the one just going by it. I was checking it for completion, but I saw this one error that popped up again and again where people thought that a mega electron volts was 1 million, or no, the 5.04 times 10 to the 6th EV, they thought that was 5.04 times 10 to the 6 volts, and it's not. And so there's actually a factor between these two of about 10 to the 19th, and that ended up making this thing smaller by a factor of 10 to the 19th. So it was down around 10 to the minus 33rd meters, but I saw somebody had 10 to the minus 44th meters on there, and I don't know just how that happened. This one, a lot of you kind of went around Robin Hood's barn to solve this thing. And it didn't need to be that hard. You had the electric potential being 0.625 volts, and the electric field was this. And the expression for the potential is K Q over R. The expression for the electric field is KQ over R squared. And if you just imagine dividing this thing by this thing, the K's and Q's, well, you're going to invert and multiply, and you'll end up with V over E is going to equal KQ over R times R squared over KQ, and things simplify a ton. This is just equal to R. So just take 0.625 volts, divide by 9.06 times 10 to the 7th volts per meter, and you'll end up with units of meters, and you'll end up with R. And so you can figure out how far from the ion you are. And then with the how many electrons did the ion lose, a lot of you got that the charge of the ion was something like 2.99 times the charge of an electron. Well, electrons only come in single units, so you can't have 1/100th of an electron. So there's some round off error, either in this thing, or maybe when you put the numbers into your calculator, you might have recopied them. Usually when I do a calculation with something like this, like the V over E, I just leave that number in my calculator to figure out, to have R stored to however many significant figures it was. And I think when you just took the 3 figures that showed up on this, you ended up with 2.99 electrons, which has to be 3 electrons. There has to be some round off error, because the atom can lose 1 or 2 or 3 or 4 electrons, but it cannot lose a fraction of an electron. So that's something you have to watch out for. Okay. Are you able to go through number 2 on the lab workout sheet on Gauss's law problems that you handed out last week? I can call it up and have a look at it. Let's see, that would be under labs, I think. Help, bring me my mouse back, or cursor back. There it is. Labs, Gauss's law. There it is. Okay, let's see, Alyssa, I think you were asking about this. There's a number 2 in Roman numeral 1. There's a number 2 in Roman numeral 2, and there's a number 2 in Roman numeral 3. Which one do you mean? Or is it Roman numeral 2 that you? Yeah. Well, while you're thinking about that, I'll print it off. And I think I've got one that's not spread out for. Oh, there's also a number 2 in Roman numeral 4. Good grief. I really made you guys suffer, didn't I? Okay, now this is not going to be blown up. So, okay, print both sides, flip pages on the long edge. Yeah. Oh, that was the rest of that homework assignment. Oh, under Roman numeral 4. Okay, should be spitting out here pretty quick. Okay, this is one that'll make you think, won't it? Number 2. Okay, so you've got this charge distribution that has some symmetry. Conduct a Gaussian surface that will allow you to determine the electric field at all points in the given space. Okay, so we have charge distributed throughout the volume of a sphere of radius r, isotropically, such that the volume charge density depends on the distance r from the center according to rho, that's the charge density, equals br squared, and B is equal to 85 nanocoulombs per meter to the 5th. Good grief. And we're supposed to use Gauss's law to determine the electric field for positions r less than or equal to r, and then for little r greater than r. So once we get outside of this sphere that has a radius of 0.20 meters, then what we have is just a big ball of charge that's got some specific charge on it. And outside of that region, it acts like a point charge. And so outside the sphere, the electric field is just going to be, it'll be radially outward. So we could write it as a vector here, but it's going to be K Q total. That's the total charge on the sphere over r squared in the r hat direction. So that's an expression that'll tell you the electric field everywhere, but you have to know what Q total is. And so that's not so simple. So I'll show you how you can figure out the charge inside a radius that's within the sphere and then the total charge on the sphere. And we'll settle that thing down. Okay. We've got a charge density within that sphere that's equal to br squared, and b is a particular an actual number, so it's going to be 85 nanocoulombs per meter to the 5th, which is unusual units, but actually r squared is going to have units of meters squared. So if you multiply meters squared times whatever the value of b happens to be, oh, that is b. If you multiply that by meters squared, you end up with nanocoulombs per cubic meter, and that's charge per unit volume. But it increases in strength as you get away from there. So let's first imagine, let's see, where's my circle drawer? There it is. Yeah, I guess that'll work. Okay, that's going to be the center of the sphere. That's not the outer surface of the sphere. I'm going to make the outer surface of the sphere bigger, and going to imagine this is just some little distance r here within the sphere. This is going to be the total volume of the sphere, and this will be the total radius of the sphere. That's going to be 0.20 meters. So let's figure out how much charge there is within a sphere that is less than 0.20 meters in diameter. Well, what I have to do is calculate this will be Q as a function of R less than 0.20 meters is going to equal, sorry, that's really messy. I'll try that again. Q as a function of R, where R is less than 0.20 meters. Okay, will equal the integral of rho dV, and the volume is going to be from 0 to some R that's less than 0.20 meters. Okay. So I'm just going to leave this in terms of R, and if you want to know the actual charge within that, then you stick in a numerical value for it. But rho is that BR squared. Okay, so we're going to have BR squared, and I'm going to integrate 0 to R, some value R. But what's dV for a spherical distribution? Well, you pick a spherical shell that has a thickness dr. Thickness dr, area is going to equal 4 pi r squared. That's the surface area of a sphere. And if you multiply that surface area times a little thickness dr, you get a volume dV. That'll be our little volume element. And that's something that's handy when you have spherical symmetry. So in this case, we're going to have 4 pi r squared dr. And now remember, b is just a number. 4 and pi are just numbers. So what this thing ends up being is 4 times pi times b times the integral from 0 to r of r to the fourth, because I've got r squared times r squared dr. And it's been a while since I took calculus, but I think that's r to the fifth over 5. And so this charge, as long as you're within the surface of that thing, is going to be given by an expression that looks like 4 pi b and r to the fifth over 5, and evaluated at 0 and some r, so it's just going to be r to the fifth over 5, and that looks to me like 4/5 pi times b times r to the fifth. Okay, now you're supposed to figure out the electric field at those points. Well, if you want the electric field here, like right there at this distance r, all that matters, you pick a Gaussian surface here that is at that radius. And it's got spherical symmetry. And so you'll be doing a calculation like this. You integrate over this closed surface here that's got a radius r, and it'll be E dot dA, and that will equal the charge that's enclosed by that thing divided by epsilon naught. Well, we just figured out how much charge was enclosed by that thing. And so we can have that. And now for this Gaussian surface, which is going to be a sphere, E and dA will point in the same direction. E should be the same strength everywhere on this sphere and pointing away from it because we've got spherical symmetry. And as long as we're the same distance from the center of the sphere, the electric field will have the same strength. dA is going to point in the same direction for every little chunk of area of this thing. So dA points that way too, and E dot dA becomes EdA. E can come outside of the integral, and I'll have E times the integral over this closed sphere of dA. That's the surface area of a sphere. So E times this, wild guess what that's going to be? I think I used it before. It's the surface area of a sphere. So this will just be 4 pi r squared, and then I'll have this Q enclosed over epsilon naught, but Q enclosed is that. So that'll tell me the electric field. So that's within the sphere. Then at some point, actually, if you want to know the total charge on the sphere, all you have to do is stick 0.20 meters in here for R. But remember, it's raised to the 5th power, and multiply it by B and then 4/5 pi. That'll tell you the total charge on the sphere. And outside the sphere, it acts like a point charge. It doesn't matter that it's got a radius of 0.20 meters. All that matters is that it has a particular amount of total charge. It's spherically symmetric. And outside there, for the electric field or electric potential or whatever, it acts like a point charge of whatever value you get when you plug in R equals 0.20 meters. So I kind of maybe did too much work for you there, but usually people don't complain about that. And yeah. Let's see. Any other questions? Let's see. Oh, is there anything else that's not showing? I haven't scrolled down in that box for a while. What about when R is less than R? Oh, that's what I was talking about. This is the expression for when R is less than R. You're going to just have to leave it. You're not going to solve for a numerical value for the electric field. For R less than R, you're going to have a value that has R as a variable. So you're just going to have, within the sphere, you'll have E as a function of R, and this will be the charge that's enclosed by the thing. And that's what I was just talking about on this part here. You'll be going through the E dot dA thing, and it'll equal Q enclosed over epsilon naught, but Q enclosed is what we figured out here. So you've got some algebra to do on that, but shouldn't be too terrible. And this will be the integral of the area over the surface of a sphere of radius little r. So it's the surface area of a little radius r. Yeah, you can only do an integral of this type out to r equals 0.20 meters, and then there's no charge beyond that. And so after that, you don't worry about it because you know what the charge is within your Gaussian surface. It's going to be whatever amount you get here when you set r equal to 0.20. And remember that B that had units of nanocoulombs per meter to the fifth. When you stick R, which is 0.20 meters on the surface of the sphere, equal to 0.20 meters, you'll get meters to the fifth. Multiplying by B, you'll end up with some number of nanocoulombs, which you'll then multiply by 4/5 pi. And that'll tell you the total charge on the sphere at that point. But if you're within the sphere, you can't get a number for it because R is going to be a variable. You could pick particular values of R, but it wants the electric field for all R less than 0.20 meters. And so you can only have an expression, an equation that describes it as a function of R. So. Yeah, that Gauss's law handout is one that makes you think. It's not all simple. There are a bunch of kind of mind-bending things on there. But a lot of it's just geometry or logic concerning Gauss's law. Oh, let's see. There was another one on homework 2 that I think it might have been 4, where you were charging you have a negatively charged plastic rod. How can you use it to place a net negative charge on a metal sphere, initially neutral, on an insulated stand? How can you use it to place a positive charge on the sphere? Okay. Now, to put a negative charge on there, you've got this metal sphere on an insulated stand. Oops, I need to draw the sphere first. So here's the metal sphere. Here's the insulated stand. So that's an insulator like plastic or something like that anyway. And then you have this rod that plastic rod, and it's got negative charge on it, and it's a non-conductor. Okay. Well, I can charge up plastic rods at school. In fact, I do that sometimes. I've got some rabbit spur that I rub on these plastic rods, and then I can do some electrostatic demonstrations with them. And if I want to put charge on something with that plastic rod, I don't have to do anything fancy. Once the charge is on there, I just wipe it off onto the metal sphere. And if I touch some part of the plastic rod to the metal sphere, that part of it will lose its charge. So if I want to transfer as much charge as possible to the plastic sphere, I'll touch this end of it and then just wipe the rest of it along there, and then rotate it a little bit in my hand and do the same thing again. And the more of this surface that I can actually bring into contact with the metal sphere, the more charge I can transfer to that thing. And so that's all you have to do to put negative charge on the thing. Now, to put positive charge on it, you recognize that this thing is a conductor. If I bring this negatively charged metal thing over there, it's going to drive electrons away from the side nearest this thing. And so I'll get, even though this is overall neutral at the time, I'll get a bunch of negative charge over here, and that negative charge left here, and so it will leave behind positive ions. Okay. Well, when I do that to put negative charge on, these things love electrons. They just lost a bunch, but if I wipe these electrons off onto it, they'll take them. And so now I'll have neutral atoms here and negative atoms there. And then when I pull it away and bring it back, it'll drive electrons away again because the other side still has negative electrons on it and so forth. But if you want to make this thing positively charged, I bring it near without touching it, and then I can take a wire, and it turns out it doesn't matter where I connect this wire to the sphere. If I connect it to ground, the charges will sense in a way that no matter where that wire happens to be attached going to ground, and by the way, this is a symbol for electrical ground. It's a bunch of slowly shortening wire or straight lines. But when I do that, electrons will flee, getting as far away from these electrons as they possibly can, and they'll flee to the ground, earth ground. And then once you've held it here for just a fraction of a second, you can disconnect the wire, and you've got a sphere that is short a bunch of negative charges because they all ran away to ground, and so it'll be positively charged. And that's how you can put positive charge on there. Ground, as in earth, is something that in any house you live in, there is a copper rod. A lot of times it's, maybe half an inch in diameter, and it'll be driven into the ground. And for certain electrical things, well, almost every outlet in your house is connected to that ground. And if there's too large a current flowing, it'll send excess charge to the earth. It can also pull excess electrons from the ground if they're needed. And so the earth is this big source and sink of charge. And there's circuits called ground fault interrupt. They're GFCI, and I always forget what the C stands for on those, but anyway, if those circuits detect too large a current, they shut themselves off, and they have them in bathrooms a lot of times, and they'll pop on you, and you have to reset them if you want to use them again. That's so if someone's listening to the radio while they're taking a bath and the radio's plugged into the wall, and they accidentally drop the radio in the bath water with them. Rather than getting electrocuted, the circuit breaker will pop in that case and save their lives. Okay, number 7 on the practice test. Where is that one? What did I do with that practice test? I don't remember. It's still on small paper. Practice test there, spring 2021 practice test. The 6B and C. And 7. Is that number 7 for you? An electron traveling with an initial velocity equal to V naught, 8.6 times 10 to the 5th meters per second in the I hat, enters a region of, boy, these equations aren't lining up nice. Does that look like the number 7 that you have? Or not? No. Okay, what is your number 7 about? Oh, and a Geiger counter. Okay, that may be the number 6 on this test. Let's see. Does it look like in a Geiger counter, there's a central wire inside a metal cylinder. You may treat the central wire infinitely long. Okay, the electric field is given by that. Okay, good to know. Hopefully that's the same one as you. Central wire has a radius that I just crossed out, but it looks like 0.203 millimeters. And the metal cylinder has a radius of that. Okay. Use the expression for the electric field to determine the potential difference between 2 points R1 and R2 inside the cylinder such that R W, the radius of the wire, is less than R1, which is less than R2, which is less than RC. Okay. Perform an integral to show that this potential difference is. All right. Well, V of R2 minus V of R1, that's going to be a delta V. That will equal the negative of the integral of E dot dl. Okay, and this way of calculating potential difference works whenever you've got an expression for the electric field. So we'll have that. Now, the electric field here, I'm going to leave it as E is going to equal 2K lambda over R along R hat. And this has cylindrical symmetry. So R hat is going to be a unit vector that points from the center of the wire outward. And so that's the direction it points outward all the time. All right, well, I'm just supposed to get the potential difference here. So dl here is just going to equal dr in the r hat direction as well. So E dot dl, when I get, is going to equal, I can put the scalars out in front of the vectors. I'm going to have this dotted with that, but the scalars can get moved. So I'll have 2K lambda over R times dr. Now that's just a multiplication dot. It's not a dot product dot, but I'll have R hat dotted with R hat. And anytime you dot a unit vector with itself, it's just 1, because it's the magnitude of this, 1, the magnitude of that, 1, and the cosine of the angle between them, the angle between them is 0, and the cosine of 0 is 1, so it's 1 times 1 times 1 is 1. So the E dot dl part of this just turns into 2K lambda dr over R, and so my delta V in this case is going to become minus, I can pull out the 2K lambda because it's constant, and inside the integral I'll be going from R1 to R2, I think. Yep, R1 to R2, and integrating dr over R. Well, that doesn't look so bad. In fact, this looks like delta V is going to be minus 2K lambda natural log of R evaluated at R1 and R2, which will be natural log of R2 minus natural log of R1, but that's the natural log of R2 over R1, that property of logarithm. So minus 2K lambda natural log of R2 over R1, and I think that's what I was supposed to get. Yeah, show that the potential difference is that. Okay, did you want to see part B? Probably. Okay, where did it go? Oh, here's B. The expression you developed in part A is good for R values between RW and RC, the radius of the wire and the inner radius of the cylinder, if the potential difference between the central wire and the metal cylinder is 1,640 volts, with the central wire being 1,640 volts higher than the metal cylinder, determine lambda. Oh, okay. Well, I can use this expression, and if I just set the outer one equal to the radius of the cylinder and the inner one equal to the radius of the wire, so then I would have delta V in that case would be, actually, this would be V cylinder minus V wire in that case, and it would equal minus 2K lambda natural log of R cylinder over R wire, except they said the central wire is 1,640 volts higher than the metal cylinder. So I'm actually doing this thing in the wrong order. So if I multiply this whole expression by -1, I'd have V wire minus V cylinder is equal to 2K lambda natural log of radius of the cylinder over radius of the wire. And whoops, this is supposed to be a V for the wire, potential of the wire. All right, now this is 1,640 volts. So 1,640 volts is going to equal 2 times K times lambda times the natural log of the cylinder has a radius of 8.53 millimeters. And I don't have to convert units, yay, because I've got a ratio in here. And the radius of the wire was, I think, 0.203 millimeters. So this is just a number. This is just a number. The only number I don't know is lambda. And so lambda would equal 1,640 volts. And I may want to write this as a joule per coulomb. We'll see. I probably will. And then on the bottom, I'll have 2 times K, which is our 8.99 times 10 to the 9th Newton meter squared per coulomb squared. That's 2K. And then I've got the natural log of that thing. And I don't think I forgot anything. Natural log of 8.53 over 0.203, and the units divided out, so I don't have them anymore. All right, so anyway, you'll end up with lambda. Now, what are the units of it? I have to do some creative stuff down here with these units. And I've got Newton meters squared, but if I write that as Newton meters times meters over coulombs times coulomb, this is a Newton meter per coulomb. That's a joule per coulomb. And so, and I can cross those ones out. I've got joules per coulomb on top, or volts, and a joule per coulomb on the bottom, but I've still got a meters per coulomb on the bottom, which when you invert that and multiply it by the time, or the top, you end up with coulombs per meter for the final units for this expression, which is what I'd expect for a charge per unit length on a wire is coulombs per meter. And then the last question, an electron is knocked loose from an atom 3.95 millimeters from the surface of the central wire. Got to be careful with this one. If it travels to the central wire unimpeded, how fast will it be going when it strikes the wire? Well, this is another potential difference problem. The electron will be traveling through a region with a particular, excuse me here, particular delta V. And well, we had an expression for this. Yeah, it's going to be going from V initial is going to be 3.95 millimeters from the surface of the central wire. That's going to be V of, well, actually, let's figure out R initial first. R initial 3.95 plus 0.203. At least I think that's 0.203, which is okay. I'll have 3, which I'm going to drop. I'll have 5. I'll have 9 and 2 is 11. Carry the 1, and that becomes a 4. So 4.15 millimeters is where it starts off. Okay, and then our final for this electron is going to be right on the surface of the wire, 0.203 millimeters, and we'll have that. And there will be a delta V in this case. It's moving in the positive direction for delta V because it's going toward the wire. Toward the wire is a decrease in electric potential energy for an electron. It would be an increase in electric potential energy for a proton. But delta V then will end up being minus 2k lambda natural log of R2. Actually, if I change this, I can put the trying to wrap my head around this. Oh, I better stay safe here. V of R initial, which is wider, minus V of R final, which is smaller in this case, is going to be minus 2k lambda, which got figured out in the last question, natural log of R initial over R final. Now, this looks a little bit weird, but this is the expression for the electric potential energy difference when R initial is bigger than R final, but we're going in the opposite direction. Or, yeah, this is okay. This is the expression when the one up here is bigger than the one down there. So, but that's going to be the potential difference anyway. And since, yeah, this will all be positive. When I multiply that by the charge on an electron, I'll have Q delta V being negative. No, this thing's going to be negative. Multiply by that and I get it positive. So if I was taking the electron in that direction, it would be increasing in potential energy. It would be going opposite the direction the electric field is pulling it. So it'd be like going uphill in its electric field because it's got that negative charge. Even though the electric field points away, the electron, it's complicated. Anyway, here's what you can do. There's going to be the electron starts here, ends here. It's going to undergo a Q delta V here. That'll be the change in electric potential energy for it. And it's losing potential energy, but we can just think of this as in terms of absolute value, and that will equal the change in kinetic energy of the electron. So at end, I can say that Q delta V, take the electron charge and multiply it by this with the R initial and the R final that I had in the absolute value, and that will equal 1/2 mv final squared minus 1/2 mv initial squared but treat the initial as 0. So 1/2 MV final will equal Q delta V. MV final squared will equal Q delta V. So that's what you're doing, and you can solve for how fast it's going there. And this is a situation where its acceleration is not constant, because the closer it gets to that wire, the greater the acceleration becomes. So we use energy differences, and the Q delta V equals the final kinetic energy. I don't have to know the details in between. I just know that if it ends up on the wire or hitting the wire, that it'll have an amount of kinetic energy equal to this. So that's what you have to do to solve one of those. This was a complicated problem, by the way, those 3 parts. However, you do have 2 hours for this test, so that should cheer you. Any others? We've been going at this for an hour and a half. This one, number 1, shouldn't be too bad. Oh, man, this looks an awful lot like a homework problem. Number 2 does. The numbers, I think, may be the same. I seem to remember 0.625 volts. So, and I think this looks an awful lot like a homework problem too. I wonder if I was this spring quarter. No, this would have been spring of 2021. So that was a year after COVID first hit. So we've been teaching online all year that time. Well, are your minds boggled? Okay. Alyssa pointed out to me this afternoon, and actually I was working outside, so I didn't see it till not long ago, that I had forgotten to post the lecture from last Thursday, but actually I think this was more helpful than that. Last Thursday, all I did was go over the topics on the test thing and point out some of the things that were on the formula sheet and stuff, but you may find it advantageous to look at that and keep studying. I will try to get there a bit early tomorrow. I plan on, for the first hour, like from 1 to some amount of time, I was going to show you some demonstrations with magnitude, demonstrating how a magnetic field exerts a force on charges in a couple of different ways. They're kind of interesting demonstrations. And but then there'd probably be time before that, like before 1, except some of you have class before 1. But then maybe before 2 o'clock, when I could answer some more questions if you happen to have them. And so study some more tonight, maybe tomorrow morning. And I'll try not to get carried away when I write this test or select questions for it. So. Okay, I'm kind of tired. I was up before 6 today. All right, I'll stop recording and try to have this thing posted by